Hi guys, I'm back with Research Chapter 11, so this is Understanding Statistics. Again, this is kind of a complicated chapter, so don't get frustrated with it. It's really more about making sure you understand how to look at the research you're reading and not really about how to do the research yourself. So don't stress out about the math. We're going to start with probability. We've already kind of discussed this. It's used to explain the extent of a relationship or the likelihood of an event. So what we're looking for here is prediction. So probability is usually expressed as p in your equation, and it's usually a decimal from 0 to 1. So for example, a probability of 0.23 means the p is 0.23, so they're the same. And that is also exactly the same as having a 23% chance of something happening. So that's exactly what probability looks like. The null hypothesis, if you remember, expresses that there's no difference between the groups in a study for the variables included in the study. So our goal is to disprove the null. The null is kind of status quo, it's what's already happening. So the researcher needs to prove that there is a difference. The null is simply stating that the assumption that, and in that assumption that there is not a difference. There's a null for every single hypothesis out there. You cannot have a hypothesis without having a null. The null just means that what you think is true isn't true. So the cutoff point of whether or not a difference means something, or if it was just by chance, is called the level of statistical significance. And that level of significance is determined by what we call the alpha level, which is usually set at 0.05. In some studies you'll find it at 0.10. At that 0.05 level, you will see there's only about a 5% chance that the researcher made an error when reporting that the null was rejected. Okay. So here's some examples of rejected or some null hypothesis. So the cat shows no preference for food based on shape. Okay. That means the researcher was thinking the cat would show a preference for food based on the shape. Plant growth is not affected by light color. So the null hypothesis is that it's not affected. Our researcher's hypothesis is that it is affected, and so on. So the null is just the opposite of what you think is going to happen in a study. So we can infer some things and we can generalize some things from that information. So an inference is a conclusion based on the evidence. We got to be very careful when we start to infer information because an inference is not a fact. Okay. It usually takes a really high level of significance to make it more accurate. And then a generalization is the application of information in generalized situations. So the difference in the study group was deemed accurate, and therefore the difference should exist in every study group. So if we repeated this exact study again, we should get the same information. If we made our population or our sample much larger, the majority of people in those areas should get the same results that we did in our smaller study. And of course we have talked about curves already, but the normal curve is the theoretical frequency distribution of all possible values in a population. So it just means that if you have a big enough sample, we generally fall in a regular standard normal curve. So the tails are the extreme ends, so this is, I think we used in another PowerPoint, the example of grades. So if one person fails the test and one person gets a 100%, that's the tail end of this. So this would be the person who failed, this would be the person who got 100%, but the majority of us are going to get in that C range, right? Because that's where average is. So let's talk about errors. You're going to hear about two different types of errors. So type 1 occurs when the null is rejected even though it's true, meaning we found that there was a difference in what we were testing, but that difference wasn't really there. The risk of type 1 is indicated by the level of significance. So there's more risk for an error with a 0.05, so 5% chance, versus a 0.01, which is only a 1% chance. So when you're looking at a study, if the risk for error is a 0.01 and you have significant findings, it means there's really not a very high chance that there were errors in that study. So it's typically a good study. Type 2 occurs when the null is regarded as true, when we should have rejected it. So we didn't find the relationship that actually existed there. It's often caused by flaws in the research or by small sample sizes. If we increase our sample size, that relationship may have become apparent to us. This is significantly an issue in nursing studies because we usually don't have very high numbers for our samples. So this is one of the ones that you're going to want to watch out for in your nursing studies. So then we have to analyze all the data that we have. The data analysis process is literally the management of numerical data. So you collected it, now we got to figure out what to do with it. That is statistical analysis, so the technique used to actually analyze that data. And then we use descriptive statistics. So it's summarizing the information that allows us to organize data in a way that means something. Otherwise, it's a bunch of numbers, and it doesn't speak to us as researchers, and it doesn't help us demonstrate those results to the outside world. And then we use inferential statistics. So that's the process of inferring, meaning, again, we're kind of guessing, but it's a very educated guess, results from that study to the populations that we were studying. So if your study is generalizable, then we are using inferential statistics to tell us that. So let's just do a quick review on central tendency. So this is your easy ones. The mode, which is that number that occurs most often, the median, which is your midpoint number, and your mean, which is your average. The range of those is just simply the lowest score subtracted by the highest score, whatever it is that we're scoring. And then your variance is your spread or your distribution of those scores. So a standard deviation is the square root of your variance. And this is where the math comes in, but you don't have to know the math to understand what a standard deviation is. It's literally just the square root of that spread. So that's how we know how much spread there is. So a z-score is how many standard deviations is the result away from the mean. The mean, again, being the middle. So you can see in our regular bell curve here with no curve, our mean, our median, and our mode are all exactly the same. When we get a skewed data, we can start to see some changes in those numbers. But a z-score is saying how far away is this score from the mean, wherever the mean's at. So how do you know what test to use? This is really complicated. Again, don't focus on this. This isn't something that you need for this particular class. This is just kind of a generalized basis for how we decide what goes where and why. So page 311 of your Grove and Grade textbook has a fantastic little chart. I did take a picture of it. I wasn't able to find the nice version of it on the internet. So here it is, but if you would like to see it a little bit more clearly or a little larger, it's on page 311. And what it's showing you here is what's the nature of our research? Remember, are we looking for differences? Are we actually trying to associate relationships? And then what's the measurement? So most of these types of statistical analysis, I'm not sure. Most of these actually have different types of measurement. So this one, for example, is by groups, and some of these are by nominal data or ordinal data or integral or ratio. If you're not sure where you're at with those, then it's time to maybe review a couple of those statistics videos. And then we can figure out what the research design looked like. And from there, we can kind of determine which one of these statistical analysis processes would work the best for us. So again, you're not going to have to know this. It's just a good way of looking at this from a research perspective, so you can tell if the study that you're researching used a good statistic, or are they reporting on a statistic that doesn't really match what their data says. So it's just a way for you to kind of double check people's work. Oops. So we can use a Pearson product moment correlation. So that's an inferential analysis that examines bivariate correlations in studies. That basically means we're measuring the extent of a relationship between two variables. That's it. So we collect data in one sample, and then two variables are measured, and the strength of the relationship between them is examined. It does not determine cause and effect, so there's no basis here for cause and effect. We would have to use something else to determine that. But it looks like this. We have a positive correlation here, we can see a negative correlation there, or this one. It's all over the place. There's really no correlation at all. The result of this Pearson product moment correlation is a correlation coefficient, which may be significant. Remember, what we're looking for here is something that's statistically significant because it tells us it's more likely to be real. So again, what is regularly significant is not necessarily clinically significant. So just because the data shows us one thing or another that's true doesn't mean that it clinically means something for the patient. Sorry, I'm clicking too fast here. Then we have factor analysis. So that examines the interrelationships among large numbers of items on a scale. So it basically lets us sort items into categories, and those categories are called factors. We use it more to develop measurement instruments, especially for abstract concepts, so things that maybe don't necessarily have a good number assigned to them. So the example here is we have some observed variables, which include waiting time, cleanliness, and staff behavior. all of those would be in the factor called cleanliness. And then the taste of food, food temperature, and the freshness is all under food quality. So we can kind of categorize things to make them easier for us to analyze. Then we get into what's called a regression analysis. This is often used with more than one statistical tool. So sometimes you'll get a regression analysis before you get a chi-squared test or an ANOVA test, and we'll talk more about those here in a second. But it's used to predict the value of one variable when at least one other variable is already known. So, for example, here on the side, we have percentage of body fat and BMI. If we already know the BMI of a patient, we can guesstimate, according to the regression analysis, that their percentage of fat is probably, if their BMI is 25, it's probably around 30%. Okay, so it's just a analysis of the data that gives you kind of an endpoint. When the independent variable predicts the dependent variable, it's called a simple linear regression. A multiple regression analysis does study data for more than 2 independent variables. So basically, regardless of how many variables it is, it's creating a line of best fit on a scatter plot, and that's what this looks like. So we can kind of say, okay, with a BMI of 30, we know the line is going to be right about here, because that would be very difficult to tell just based off of the scatter plot. So it gives us an easier way to look at that data. I don't know why that's doing that. Okay, measuring differences. So causality is a way of knowing that one event leads to another. We sometimes use the chi-square test of independence for this, and that determines whether 2 variables are independent or if they're actually related to each other. We can only use it with nominal or ordinal data, and we need large sample size to make it work. So it's actually given to you by that x squared there, and it tells you that the author used that chi-square. And here's an example of that. And again, you do not need to know the math behind it, you just kind of need to know what this table looks like here. We can also use a t-test, and that's used to examine group differences when the variables are measured at interval or ratio level, so the difference here being the type of data that we're looking at. And you can see here, if we had a treatment, we can see the pre-treatment here, and we can see, oh sorry, it's the other way around, the pre-treatment here and the post-treatment there. So the goal here is to show us very simply, did what the intervention was, did it work? And it did. We can see here that we had higher blood pressures to start, and after the treatment we had lower blood pressures. So it's a simpler way of looking through that data. We can also do an analysis of variance, which is also called an ANOVA test, and that's used to examine differences between 3 or more groups. It tests for differences in variances, and it's actually usually reported as a F value. So we got to figure out what the total variance is inside the sample, and then we can actually see the mean within that. That gets pretty complex. Again, usually we use a Excel spreadsheet or an actual specific calculator meant for statistics for this one. Again, not something you have to measure, just something you need to know kind of what it is. And our last big one here is your analysis of covariance. And so this examines the effect of a treatment apart from the effect of one or more potentially confounding variables. So what that means is you have a variable that may or may not have affected the end result. So for example, and this is a pretty common one, it's used for pre- and post-test scores when accounting for low scores and high scores from the beginning. So for example, if you knew absolutely nothing about, let's say, signs and symptoms of chest pain. If you knew absolutely nothing about it, you're going to score pretty low on the pre-test, right? By the time you get done with a 15-minute education about chest pain, you're probably still not going to score 100% on the post-test, right? Because we just introduced you to the information. Whereas if you already knew quite a bit about chest pain, you're going to do pretty well on the pre-test, which means you're probably not going to do that much better on the post-test. So that skews our data because we're not comparing apples to apples, we're comparing apples to oranges. And so this statistical analysis helps pull those data points out so we can kind of see the differences without those confounding variables. So as we're interpreting results, a couple of key things to remember. So is it significant? If it's significant, that means it supports a logical link developed by the researcher. Significant results are realistic results. If they're non-significant, it doesn't necessarily mean they're not true, but it may result from a type 2 error, or there may in fact just be no relationship between variables. Mixed results are inconclusive due to the methodology results. We can also get unexpected results and say, oh, wow, didn't think of that. We probably need to do a new study and see if those two things are in a relationship with each other. And then clinical importance. So again, just because something is significant, it doesn't mean it's clinically significant. So if we found, let's say, a significant difference in the blood pressure of somebody taking, let's say, a blood pressure medication and somebody not taking anything but exercising regularly, we may get a 2 millimeters of mercury difference between those two test groups. That may be a statistically significant difference, but clinically it really doesn't do much for the patient. Their blood pressure is still probably too high if all we're seeing is a 2 millimeter of mercury difference. So clinical importance is something that we really have to look at as nurses to determine whether or not the study is actually worth something or not. So then we also should see a few other things in the study. So we should know what their limitations are. So for example, if the study is limited because it's not generalizable, it limits the credibility of the study. So it doesn't mean that the study is poorly done, it just means that we don't have enough data to infer that it's relevant to a larger population. So we need more information before it can be expanded. We also should have some conclusions about the study, so you shouldn't be entirely forced to rely on yourself when you're reading those statistical studies. Just understand that any conclusions the researcher comes to may be influenced by bias. So numbers can tell us a lot of different things. They don't always tell us the right things. So knowing what those statistical tests mean can help you decide whether or not that conclusion is biased or not. And then we should have some implications for nursing. So what does this mean for us in our nursing practice? Is it something we should be following? Is it something you shouldn't be following? Is it something that we didn't really find a relevant answer for? And then there should be recommendation for further study. There's very few studies out there that shouldn't recommend further study. It would have to be a huge amount of people, or would have to have been a study that's been repeated many, many times for us not to say that we need to do some further study to make sure that the results that we got are actually applicable to the whole population. So those are some things you want to keep in mind when you're talking about these types of studies. That's it for Chapter 11. If you've got any questions, let me know.